Good morning, class. I'm kind of giddy today because this section that we're covering now, it just always gets me going. It gets me excited because this is so cool. We're going to look at solar intensity. On the previous video, we looked at sun angles. And so the sun angle leads to the solar intensity. So I wanted to give you a couple of examples of calculating solar intensities and what that means in terms of weather and climate and temperature in particular. And so we're going to use Green Bay, which is located at 44.5 degrees north latitude. And we're going to look at it on 2 different days. So Green Bay on June 21st, Green Bay on December 21st, first day of summer, okay, first day of winter, summer solstice, winter solstice, okay? So you're going to have to take my word for this first part. I've done this calculation many times. And so we know that the sun angle in Green Bay on June 21st is 69 degrees, okay? So we'll draw a sun ray coming in, striking the earth at 69 degrees. Okay, and that's the highest sun angle that Green Bay will ever have during the course of the year. And again, it occurs on summer solstice, June 21st. Okay, and remember, we need to look at the surface area. Okay, and so that surface area, if you remember from the previous video, is calculated as 1 meter squared divided by the sine of the angle. So the angle is 69 degrees. Okay, and if you do the math, this comes out to 1.07 meters square. So this is the smallest surface area you're going to have is 1.0 meters square. And so this is a very intense beam. This is a low amount of surface area being covered by this sunbeam coming in. That sun ray coming in is only covering 1.07 square meters. Okay, really interesting tidbit here is that on June 21st, and about a week before and a week after, Green Bay actually has a higher solar noon sun angle than the equator has. I always thought that was pretty cool. So June 21st, sun ray coming in at 69 degrees. That sunbeam is going to be spread out over 1.07 square meters of area. All right. Now, the next thing, kind of new twist here, is that how much energy are we receiving from the sun? Well, there's 1,370 watts of energy coming down from the sun. We call that the solar constant. Okay, that doesn't change. But what does change is the surface area over time. And so we're going to take that 1,370 watts of energy and divide that up over 1.07 square meters in order to get the solar intensity. So if we look at the solar intensity, okay, that will be the 1,370 watts. And it's being spread out on this day, on June 21st, over 1.07 square meters. So what is the intensity? 1,370 watts divided by 1.07 square meters comes out to 1,280 watts per meter squared. That's a pretty intense sunbeam, okay? Even though we're at 44.5 degrees north latitude, that's a really intense sunbeam. So it makes sense that Green Bay's warmer in the summertime, okay? Because we have a more intense sunbeam. Let's take a look then on December 21st. So on December 21st, Green Bay's solar noon sun angle is going to be 22 degrees. Okay, and so you'll have to take my word for it, but I've done this calculation, I wouldn't say a billion times, but I've done it a lot. Okay, And so we've got the sun ray coming in at an angle of 22 degrees. That's the solar noon sun angle. That's the highest the sun is going to get in the sky over Green Bay on December 21st. Okay, so if we take a look at the surface area being covered by that sun ray, striking Green Bay on December 21st, again, it's 1 square meter divided by the sine of 22 degrees, the sun angle. And that surface area comes out to 2.67 square meters. Okay, so quite a bit bigger, quite a bit more surface area being covered on December 21st than on June 21st, when the sunbeam was only covering 1.07. So a very intense sunbeam on June 21st, a much weaker sunbeam on December 21st because it's covering so much more surface area. Okay, so if we look at it then in terms of solar intensity in December, that solar intensity again is going to be 1,370 watts of energy coming in, but that 1,370 watts of solar energy being spread over way more surface area. So that's 1,370 watts, this time being spread out over 2.67 meters squared. Okay, and so that means that the intensity of the solar beam on December 21st in Green Bay is going to be 513 watts per meter squared. Okay, again, compare that to what the intensity was on June 21st. Okay, 1,280 watts per meter squared on June 21st, only 513 watts per meter squared on December 21st. Okay, so if we look at this, ask the question of how many times more solar energy does Green Bay receive in summer, and in particular on the summer solstice, versus winter? Okay, so to do that, all we got to do is, here's the energy that the Green Bay receives on June 21st, 1,280 watts per meter squared. Okay, divided by how much energy does it receive on December 21st? That's 513 watts per meter squared. So if we do the math, this comes out to basically 2.5. Okay, and so Green Bay receives 2.5 times more energy on summer solstice than it does on winter solstice. And again, remember, it's the intensity that determines temperature for a period of time. So it's no wonder that Green Bay in the northern hemisphere is warmer in summer and colder in winter, because the sun angles are lower, and therefore there's more surface area as you head into winter, which then translates into a lower solar intensity and colder temperatures in winter. Okay? All right, so hopefully that makes sense to you. And if you have questions, let me know. This is the most important stuff that you're going to learn in this class. It translates so much to the resulting weather that this is, you don't worry too much about the numbers, but remember the concepts. I shouldn't say remember, understand the concepts, okay? Don't memorize them, make sure you understand the concepts of solar angles, solar intensity, and the resulting temperatures, okay? All right, next we'll talk about some other really cool stuff. That's coming up.